So now we're going to be examining how we can use differentiation to use them to really help us work out sort of problems to do in real sort of world situations. Now, the thing is, you need to remember that the derivative f dash x was defined to be the limit as delta h approaches 0, as h approaches 0, of f of x plus h minus f of x over h, which means it's equivalently the limit of delta y over delta x as delta x approaches 0, which is, of course, how we come up with our notation dy dx. But remember, what this then means is that it would represent a rate of change. Yeah. More specifically, it's an instantaneous rate of change. You know, as small changes are made in, you know, a variable, e.g. x. So a more complete answer might be saying that a derivative represents an instantaneous rate of change of a function, such as y, as small changes are made in the underlying variable, in our example here, x. And so therefore, it's applicable to all sorts of real-world examples that involve rates. Can you think of anything that involves rates in the real world?
Speed.
Exactly. So you've got, formally we'll call that kinematics. So the study of, you know, the way things move. But yes, exactly. More technically, we'll use velocity, but things like velocity and speed. Anything else?
No.
Okay, so that's a good example. So, and that's definitely something that we'll need to be looking at in today's lesson. So we've got speed, velocity, acceleration, and all the kinematics things. There are other rates though. So another thing that we will be looking, other rates might be things like, you know, chemical rates of equation, chemical reaction rates. So you won't be studying that in maths, and you won't really need differentiation in chemistry either. But just so you know, the rate of chemical reactions is properly expressed using derivatives, right? So we could also talk about, for example, any sort of thing that involves rates. So any sort of like science, population growth or decay. So any sort of biological studies. So population growth or decay. So how quickly bacteria grow, how quickly you can grow crops, or anything that sort of changes, that grows and decays. And we actually, so these are all to do with rates. So these are technically all rates themselves. And there's a whole lot more that we can do there. Now, the one we'll be focusing on is kinematics. And to some extent, we'll do a little bit of this, but a little bit later. And the other thing that we can use derivatives for, I mean, derivatives are ultimately rates, but remember we use derivatives to work out maximum and minimum, right? Of a function, right?
Yeah.
So therefore, we can also use it for optimization type of problems. So basically, we can say, subject to some constraints, maximize something. So for example, it would be like, I give you a certain amount of material, now make the biggest box with the biggest volume you possibly can. Or, you know, given these constraints, what is the fastest, you know, what's the shortest amount of time that you can get from A to B? Any simple sort of question like that could be properly solved with calculus. Okay. And these are going to be the key factors that we're going to be looking at today. Now, we will need to kind of briefly talk about what displacement, velocity, and acceleration are, but I believe we've kind of talked about that in the previous vectors class. Is that right?
Yes.
Good. That means we won't need to talk too much about it now. But just a brief recap, because you will need it for talking about our kinematics. We've got things called scalars and vectors. Now, your scalars are things that have magnitude only, and your vectors have magnitude and direction. Now, scalars, for the purposes of kinematics, you focus on distance and speed. And as a quick review, distance is just the length of the total route traveled. Doesn't matter if you go backwards, you keep adding. And speed is just defined as distance over time. Vectors are your displacement, which is defined as the straight line distance from the origin to the final position, plus direction. Now, if a displacement is basically just telling you the straight line distance from the origin with the direction, then what's another way to interpret what displacement kind of tells you? So if it's simply just telling you where you are relative to the origin, it's kind of like telling you your coordinates, right?
Yeah.
Which more or less is telling you your location or position. Like your displacement pretty much nails down where you are. Right.
Yeah.
Now, velocity, by definition, is change in displacement over change in time. And acceleration was change in velocity over change in time. And we basically said that this was the rate of change of displacement. And we said that this was the rate of change of velocity. Does that make sense?
Yeah.
Now, of course, speed is the rate of change of distance. So this is just a brief recap of everything we've done so far that we've talked about before when we did vectors with regards to the definition of these things. Now, we'll be mostly working with the vectors, in other words, displacement, velocity, and acceleration. And we won't be doing too much with, distance and speed. However, do note that questions could ask you about distance and speed. You'll need to recognize that you are working with the vectors, displacement, velocity, and acceleration. And from that, try to work out the appropriate distance and speed. So let's just distinguish some things. Do you understand the difference between average speed and instantaneous speed?
Yes.
What's the difference?
The average speed is just the average speed.
How would you calculate it?
Trying to think about it. What? Time divided by Wait, distance divided by time?
What can, like, speed is always distance over time. Could you qualify it? What distance over what time? Just to be more clear.
Change in distance?
Over what period of time?
Change in time?
Well, it's basically the total distance over the total time you're considering, yes?
Yeah.
So for the whole trip, you would take the total distance over the whole trip and divide it by the total time for the whole trip. That's essentially the idea.
Yeah.
All right, but how would we do that if we're trying to deal with, you know, instantaneous speed?
Can you just find it?
Well, it's still distance over time, right? But what are we going to do? What's the difference?
So we divide distance by the, oh, isn't this something to do with limit?
Yeah. Basically, we're going to just take a very short amount of time, right?
Yeah.
So instead of taking, like, 10 hours for like a plane trip, or 3 hours for, a trip of 30 minutes, you're just going to take like a very, very, very small period of time. Does that make sense?
Yeah.
So essentially, it's the limit as delta t approaches 0. And average velocity and instantaneous velocity are basically the same idea. So average velocity is the total displacement over the total time. And the instantaneous velocity would therefore be, the displacement, change in displacement over change in time, but as, the limit of delta t approaches 0. Does that make sense?
Yeah.
Now, because your change in time approaches 0, then just so you know, instantaneous speed is basically equal to the absolute value of instantaneous velocity. So if you ever ask questions about speed, you would basically work, like instantaneous that is, then you would basically work out velocity and then just, get rid of any negative signs that you might have.
Yeah.
Now, if it's distance and displacement, that's a little bit more complicated. You would just basically have to consider, based on the definition, think of what, has the particle changed direction. If they haven't, well, then it's the same thing anyway. If it has, then, well, you'll need to then consider how it's moved and then basically break it up and add them up accordingly. So basically, refer to the previous discussion on scalars versus vectors that we've covered before. Does that make sense?
Yep.
Good. So we've basically said, what the definitions are. We've talked about displacement. We've talked about velocity, So right now, I'm going to start leaving off very shortly the word instantaneous and just use the word velocity. If I don't put the word average, assume I mean instantaneous. So instantaneous velocity, we said, is the limit as delta t approaches 0 of change in displacement over change in time. Now, can you see how else we might be able to express this?
The derivative.
Derivative of what?
This change in displacement.
With respect to?
Time, changing time.
Correct. In other words, the instantaneous velocity is the derivative of displacement, which will now give the letter x, with respect to time, which we will give the letter t. Indeed. And so what that means then is now we're saying that if we have v equals instantaneous velocity, then considering what the definition of instantaneous velocity is, all that is really required is for you to derive displacement with respect to time. Does that make sense?
What does the green word say?
Derive with respect to time.
Oh, yeah. Yeah.
Good. Is that clear?
Mm-hmm.
So now think about this. What was the definition of acceleration? What was acceleration?
It's like when you increase the speed.
It is, but perhaps go back to our definition of what acceleration was.
Oh, rate of change of velocity.
Right. And how do you calculate rate of change of velocity?
Change in velocity over change in time.
Right. And if I want instantaneous acceleration, then what would I do?
And you derive.
Ultimately, yes. But basically, I will take a limit of t approaches 0, which means this is the derivative of velocity with respect to t, which we will now have v and t to represent. So in other words, because it's the rate of change of velocity, then as long as we derive with respect to time, then we will get a acceleration.
Yeah.
Good. Does that make sense?
Mm-hmm.
Good. So that's basically, I mean, we've kind of talked about why, but that's really the gist of it, all right? So let me just rewrite it again to stress the key points. But displacement definition is x, all right? And as we said before, the definition of displacement is that it's just going to be some sort of function in t. So note that this must be a function in t. For the questions you're going to come across, you'll basically be given x as a function of t. So, it could be something as simple as, x squared, for example. Or it could be more complicated, but it doesn't matter. In other words, you're going to get some sort of displacement. Now, if you want to work out the velocity, which we'll call v, it is the first derivative of x with respect to t. So other ways to write it would equal dx dt. And sometimes you'll see it written as x dot. So the dot here simply represents derivative deriving with respect to t. So it's kind of like a dash represents deriving. A dot just represents derivation directly with respect to t.
Mm-hmm.
which means to go from here to here, what you need to do is derive with respect to t. In other words, velocity is the first derivative of displacement with respect to time. And acceleration, which we represent by a, is, well, the derivative of v with respect to time. But because v is the first derivative, then it would alternatively be the second derivative of displacement with respect to time, and therefore written as x double dot. You might rarely see it written as v dot, but more likely you'll see it as x double dot if you see that notation. Or of course, it would be, f double dash t. They're all equivalent. Which then of course means that if we derive again with respect to time. So one thing you can take away is that velocity is the first derivative of, x, and a is, you can more generally consider it as the second derivative of x, but also, of course, you can think of it as the first derivative of v. Does that make sense?
Yeah.
Good. So remind me, graphically, what does the first derivative represent?
The gradient.
Correct. So how do we get the velocity from a displacement time graph?
Sorry, say that again.
How do we get the velocity from a displacement time graph? If I've got a graph which represents, which has got a displacement against time, how do I get the
Yeah, you derive it.
Yeah, but let's say I don't know the function. Let's say I just draw it out. Then how would I get the velocity?
Oh, you find the tangent.
Right, it's just the gradient. And how would I get the acceleration?
Well, you derive it again.
Well, you don't know the function.
It's just the rate of change of the velocity one.
So what would it? So if I have a displacement curve, how do I find out what the acceleration is like? What do I look for? It is the second derivative after all.
The concavity.
Yeah, exactly. It's the concavity. So, I mean, we'll just quickly give you some examples here. We'll start simple, but let's just say we've got 3 graphs. We use different colors. So most likely in this topic, you'll unlikely come across an AT graph. You're much more likely to come across an ST graph more than anything else. But this is basically a displacement time graph. I'll use X because in this topic, it's more X rather than S. So this is your displacement time graph. This is your velocity time graph. And this is your acceleration time graph. Now, because of what we discussed earlier, then quite clearly, you can probably, by definition, the y value here is clearly going to be displacement. I mean, that's what the axis says, and that's what the title says. And the y value is going to be velocity, and the y value is going to be acceleration. That much is obvious. But by definition, because velocity is the first derivative of displacement, that must mean the gradient must be, well, velocity. And the gradient of this must be acceleration. And so as a result of this, if I have a straight line as my displacement time graph, then what can you tell me about the derivative of a straight line?
It's just the gradient.
And in this case, what will the gradient be? Just roughly. What sort of thing?
3.
All right, yeah, it's a positive constant, right?
Yeah.
So that means your velocity will look like this, something like that. And it won't change. And what will my acceleration be then?
0.
Correct. So blue is one set of possibilities, right? You could have a straight line displacement time graph. You will then get a horizontal line for velocity time, and therefore that means acceleration will be 0. But of course, often things aren't quite so simple, but that's just the general gist. What if I had a horizontal line, but a positive value for acceleration? What would that tell me about my velocity time graph?
It will look like the displacement time graph.
All right, so then what would happen to the displacement time graph?
Maybe like a half a parabola.
Yeah, pretty much. So in other words, in my example here, this was linear. Well, it was parabolic. You can have a parabolic, or quadratic as your expression for your displacement, but that implies you'll have a linear velocity time, which implies you'll have a constant acceleration, which is all true. Or you could have a 0 acceleration from a constant velocity, which comes from a linear displacement time. Does it make sense?
Yep.
Now, this is jumping ahead a little bit, so I won't really focus on it too much. But I just want to say that, while we've got these things sort of drawn out, the area under the curve represents the change in displacement. So basically, the area represents the change in displacement, and the area represents the change in velocity. When we do a bit more calculus, we can sort of tie that in as well, but I just want to quickly mention that here. So you can see here, if, for example, in the blue line, there's no change under the sort of blue line, so the velocity doesn't change at all. Here, the area, is sort of increasing, so that's the change in velocity is increasing at a constant rate. All right, so let me quickly do an example question, and I will leave you to do the rest for homework. So, for example, if we have all right, so as I had mentioned, you'll only be able to do questions for functions you can derive at the moment. It's 5t squared, so x equals 20t minus 5t squared. So if you see any sort of exponential, any log, any trig functions in your functions right now, you won't know how to do them right now, but you will know how to do them later. But as far as the concept of deriving displacement with respect to time to get velocity, and deriving velocity with respect to time to get acceleration, and solving questions like that, we will kind of do questions like this. And this might be sort of representative of like an exam question. So obviously this, I'm breaking it down a lot, but basically this could, be an example of what you could be asked in an exam for this section for a question like this. So basically you start with the fact that x, which is displacement, equals 20t minus 5t squared. Now, it asks you to find v and a, velocity and acceleration, as function of t. How would I find velocity as a function of t?
Derive it.
What's it?
20t minus 5.
Right. You derive displacement, which in this case is 20t minus 5t squared, and that gives you your answer for v. Does that make sense?
Yeah.
All right, how do I find a?
You derive v.
And that's that. And that's a is done. Any questions with that?
No.
Right. Now, for the rest of this question, it's really a question of if you're comfortable with looking at the question and working out what they want you to work out and how to work that out. For some students, it's really easy. For some students, they will struggle a bit more with this. And so just to see where it falls for you. But think about this. Read the question and think about what it means. You are asked to find the initial speed of the ball. Can you translate that into mathematical terms for me? Find what?
Find the initial speed.
True. You want to find the initial speed. So are we looking for like displacement, velocity, or acceleration, or none of them?
I don't think it's acceleration.
It's not acceleration.
Or displacement.
So what is it?
Velocity.
It's basically velocity, right? We said speed is the absolute value of velocity.
Yeah.
So it's basically the absolute value of velocity. It's basically velocity, right? At what time though?
0.
Yeah, exactly. So rephrased, you're basically finding v when t equals 0. Does that make sense?
Yeah.
And how would we do that?
So v equals to 20 minus 0.
Yep. And then?
And then v equals to 20.
Yeah, you sub t equals 0 into v. Then of course, v equals 20 at t equals 0. Therefore, initial speed is 20 meters per second. Try to also answer with units.
Yeah.
Now, C. Again, think about what it's asking. Find when it returns to the ground. So what are we asked to find?
The time?
Right, find t when?
When x is 0.
Exactly. As long as you can read the question and understand what you need to do, that's basically it. If some students struggle a lot with that, but it's actually not as hard if you understand what each letter represents. So find when, which means solve for t. When it returns to the ground, well, x is your height above the ground. So basically you just, find when it returns to the ground, which means you let x equal 0 and solve for t. So that just means 20t minus 5t squared equals 0. Of course, you need to know how to solve for your derivatives, your quadratics, I mean. It's just your standard question, really. So we get two answers, t equals 0 or t equals 4. So when does it return to the ground?
4.
Exactly. Right. D, show that the speed at which it returns is equal to its initial speed. How will we do that?
Oh. Well, something equals to 20.
So basically show that the speed is equal for both t equals 0 and t equals 4. Well, we already know, because from b, that it's 20, right? So we'll basically sub t equals 4 and, find v. So v will equal 20 minus 10 times 4, which is negative 20. Speed will equal absolute value of v, which is 20. Therefore, it is the same speed.
Mm.
Does that make sense?
Mhm.
Good. So E, find the maximum height it reaches. How do you find the max height?
How do you find the maximum?
Sorry?
So you find it when the time equals to 2?
Well, it will be, but why is it t equals 2?
Well, because it takes 4 seconds to return.
How do you know it's halfway? Which it is, but how do you know?
That's true. I don't.
So you are correct, and it is halfway and it is symmetric, but I think you should basically look at it from the point of view. You can either look at it from the point of view of physics, which is if you kind of throw the ball up, then it will get slower and slower and slower, but it'll go up, right?
Mm.
Until it reaches the maximum height, which is when it stops, and then it starts coming back down. Which means at the maximum height, the velocity will equal 0.
Oh, wow, cool.
Because it's going to, keep going up until it kind of stops and then starts coming back down. The other way to think about this is that, well, we haven't really talked about optimization. So I'll leave that other way after we've talked about optimization. So we were going to talk about optimization today, but we haven't really had the time to. But just thinking about it from the physics point of view, you throw a ball up, it will go up, but get slower. But, it's still going up, right?
Yeah.
So, but when it stops going up, it will have to stop before it starts coming back down. So we'll need to let v equals 0 at max height. We'll need to find the t, and then sub the t into x. So we'll just quickly do that here. So we will let 20 minus 10t equals 0, which means, of course, t equals 2, as you said. So this is, t equals 2 at max height. And then x must equal 20 times 2 minus 5 times 2 squared, which is 40 minus 20, which is 20 meters. So 20 meters is the max height. And we've actually already done F.
Yep.
Great. Any questions with that?
No?
Good.